Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. So we have finished 9 modules until up to now, and now we are beginning with 10th module, and this one, just like the last one, this one also will be dedicated to X-ray diffraction. And in the last module we discussed about history of X-ray, then generation of X-ray by continuous spectrum, characteristic spectrum and all of this, and then we just started discussing about the absorption, X-ray absorption, and there we have discussed about mass absorption coefficient, linear absorption coefficient, and then also we discussed about the absorption age, how it happens, like by scattering, by true absorption and all of this. We started discussing about that. We discussed about the fluorescent radiation, how fluorescent radiation occurs, fluorescent yield, and then we discussed about OJ electron generation and so on and so forth. So, we will be continuing that discussion about X-ray absorption in this lecture as well, and we will be looking again X-ray absorption. We will be discussing about absorption age and the relationship of absorption age with characteristic radiation, and if time permits we will also be discussing about X-ray filters. Okay. So, X-ray absorption, we have already seen that this how the mass absorption coefficient varies with lambda, that is the wavelength of the electrons, wavelength of the X-ray, and what we have seen is that like this has 2 branches, that mass absorption coefficient variation with lambda, this has 2 branches, one in this side, one in this side, and they are separated by a sharp discontinuity within a very fixed and very narrow wavelength range, where the mass absorption coefficient increases by manyfold. So, if we now consider, and this is I told that this is basically for nickel, something like a nickel material, but this is very typical for any other metals, and it depends, obviously the wavelength depends on the atomic number of the elements, but this basic shape and the presence of characteristic presence of absorption age, this does not change, or this does not depend on the materials. The shape and the wavelength, this may change, but the shape does not change for material. All the material, most of the metals will have this kind of a absorption relationship between mass absorption coefficient with the wavelength. So, the first thing now we can see, if we use X-ray of wavelength 2.5 angstrom. So, this is, let us say this is the incident wavelength of the X-ray where we start, and initially what we find that this is a nickel, as I said, this is a nickel sheet. So, initially what we find that the X-ray intensity, the mass absorption coefficient is continuously decreasing as the wavelength is continuously decreased. Okay, wavelength is decreasing continuously and the mass absorption coefficient is also continuously decreasing, and the relationship we already discussed about that, mu by rho equals k lambda q zq, where k is a constant, lambda is the wavelength and z is the atomic number. Okay. So, at first the mass absorption coefficient here, when we begin with around 2.5 angstrom wavelength X-ray source, there the mass absorption coefficient was around 180 centimeter square per gram. So, this is as we discussed that basically this is a linear absorption coefficient, and the unit of linear absorption coefficient in centimeter inverse, and this is the density. So, the unit of this density is gram per centimeter cube, and together if we do unit analysis, then we will come that dimensional analysis will give us this is to be the kind of unit for absorption coefficient, mass absorption coefficient. Okay. Now, if we decrease the wavelength here, what will happen? The energy of the electron will also increase correspondingly. So, it is shown here, when we are decreasing this wavelength continuously, the energy of the electrons will also goes higher and higher. Mass absorption coefficient also similarly decreases as per this wavelength decrease, as per the increase in the energy, because now if the electron or if the X-ray quantums or X-ray photons, when they become more energetic, they can easily pass through the absorber. The material which is there, they can very easily. So, it is like hitting if you have a ball, if you have a wall, you are hitting it with some kind of a ball. If the ball has a higher energy, it can just penetrate through, it can break the wall and go through on the other side. If it does not have that much of energy, it will be possibly absorbed within the wall itself. So, that is what is happening. The X-rays, as soon as the wavelength decreases, energy of the X-ray increases, and those X-ray photons will now be able to pass through the material, resulting in a decrease in the mass absorption coefficient. Okay. Now, when the wavelength is reduced below the critical value, that means the absorption age, K absorption age, and here for nickel this K absorption is lambda K equals 1.488 angstrom. So, as I said, this is very narrow, in the absorption age is very narrow, and the wavelength is quite fixed, just like the characteristic X-ray radiation. There also the wavelength is, the spread in the wavelength is very narrow, and it is very well defined for the material. So, here same thing, this is very well defined for any element, this does not change. If you change the let us say if you change this X-ray the source, and then also this remains pretty much basically the same, it only depends on the wavelength. Okay. Now, the K absorption, the mass absorption coefficient, now if you decrease and if you bring the wavelength value close to this K absorption age, what you will see is that there is a almost 8-fold jump in the mass absorption coefficient, and this jump is basically because of the K absorption, true K absorption is happening. This is not, as we already discussed, scattering is another possibility, but that is just a possibility for light elements. For heavier elements, it is mostly the true absorption that happens. So, true K absorption now started happening at this particular lambda K, and this transmitted a large fraction of the of incident X-ray quanta is taken up, or the energy is taken up from the incident X-ray beam. A large amount of energy is taken up in this true K absorption process. So, that means the transmitted radiation on the other side, that will be having much lower energy or much lower intensity compared to the incident X-ray if the wavelength falls within this K absorption age. Okay. Now, this true absorption, we know the true absorption process, two things happen. Number one, a photoelectron is generated, and second thing, and fluorescent radiation is generated. So, the energy of the incident X-ray, that is lost here in this K absorption, near the K absorption age, the incident energy of the incident X-ray which is lost, that is, we can equate it to the energy of the fluorescent radiation plus the energy, kinetic energy of the photoelectron. So, that is how the energy loss happens near this K absorption age. From this, since this entire energy has to be conserved in the process, now the energy per quantum of the fluorescent radiation, that means this fluorescent radiation energy has to be lower than the incident X-ray energy that is lost here because of the K absorption age. Okay, and that is very justified also, because it is fluorescent radiation plus the kinetic energy of the electron where this incident energy is going. This also means that the energy for this K absorption age, if we think of that, this incident X-ray energy, what the part of the incident X-ray energy what is lost in this K absorption, 2K absorption process, then this K absorption age, the energy required to produce this K absorption age, this will also be greater than the energy required to create a characteristic radiation, because remember I said the fluorescent radiation is basically nothing but a characteristic radiation. Only difference is fluorescent radiation is caused by an X-ray photon, whereas characteristic radiation is caused by an bombarding an electron, but the energy between them is basically pretty much the same, because they are both generated by K shell vacancy and then another electron jumping from higher energy, higher electronic state. That is it. So, the amount of energy between these electronic states decides the energy of this K K characteristic radiation or this K fluorescent radiation. So, that is fixed for both of them. So, now if we start from there with that relationship, that the incident, the energy change in the K absorption age is greater than the K characteristic radiation. What we can then confer is that the wavelength of K absorption age here, this is the wavelength of K absorption age, this must be shorter than the K characteristic radiation of that particular metal. In this case, it is nickel. That means the lambda K absorption age will be lesser than the lambda K characteristic radiation. That means the lambda K characteristic radiation will be somewhere over here, just before the K absorption age, because there is this photoelectron, this part is also involved, the photoelectron energy. So, the amount of energy lost in the true absorption or in the absorption process is bigger or is greater than the amount of energy required to produce the K characteristic radiation, and in the process the absorption age appears at a shorter wavelength compared to the K characteristic, compared to the wavelength where the K characteristic radiation is produced from the same metal. Again, remember, the absorption age is produced by the X-ray signal, whereas characteristic radiation is produced by normally by an electron, can be produced by if it is a fluorescent, can be produced by X-ray, but the absorption age is only related to the X-ray signal. Okay, so that is why these two are different, even though the process looks same, but these two are little bit different. Okay. Now, this 8-fold increase, as we already said, so in the K absorption age there is almost like an 8-fold increase in the mass absorption coefficient. This means there is a huge change in the intensity. The change in intensity is somewhere over here, just before reaching the K absorption age. The change in intensity, if that is around 0.1, this is called the transmission factor, Ix by I naught, the ratio between the intensity of the transmitted X-ray by the intensity of the incident X-ray, and we can calculate this from simply from this equation, Ix equals I naught into e raised to the power minus mu by rho into rho x. From there we can calculate Ix, and if we know the incident X-ray, and we can measure this also, we will come to that. So, if this is around 0.1, that means only 10% of energy transmission or only 10% of the incident X-ray is getting absorbed just before reaching lambda K, then this is around 10 raised to the power minus 8 for any wavelength just shorter than lambda K. So, between this wavelength and between somewhere over this wavelength, there is a huge difference between the X-ray absorption process, the amount of X-ray that is getting absorbed. Okay. So, this is the importance, one of the importance for the X-ray absorption age. Okay. Now, as we decrease the wavelength below even shorter, so we started from here, we have seen that when we decrease the wavelength continuously, the X-ray continuously the mass absorption coefficient decreases, and this decrease is purely because X-ray energy is increasing and the X-ray, most of the X-ray is just passing through without getting absorbed. And near to the X-ray absorption age, when we hit the X-ray absorption age, huge increase in the mass absorption coefficient. Okay. So, what happens when we decrease the wavelength even further? Now, the energy is sufficient. So, energy reaches the critical excitation, critical value, and the critical value means the value or the energy of the incident X-ray photon is now enough to produce photoelectron and fluorescent radiation. So, if we decrease the wavelength even smaller, that means if we increase the energy even higher, the process will still continue. The production of photoelectrons and production of fluorescent radiation will still go on, but the mass absorption coefficient will continue to decrease. Okay, and this is because and we can see for the same nickel sheet here, that at a wavelength of around 1. So, right now here the incident X-ray quanta is very energetic. So, the energy of the quanta will be so much that again the same thing will happen. It will just pass through the some part of it will definitely cause the true absorption, but most of the X-ray photon will be so energetic that again the same thing will happen. they will just pass through the material without causing any kind of change, any kind of true absorption. So, basically if you check the mass absorption coefficient of something like 0.1 or something like 1 lambda of 1 angstrom versus something like lambda of 2 angstrom, this is pretty much the same. The only thing happens between them close to this K absorption edge, and both sides here and here the mass absorption coefficient is decreased because of the increase in X-ray energy. That is it. Here only the true absorption and scattering, all those processes are valid. In these two regions, it is only decided by the energy of the X-ray. If the energy is too high, they will simply pass through this material without getting absorbed. That is it. Okay. Now, what happens if we go in this side? So, we have seen in this side. Now, what happens if we go on this side? If we use an X-ray signal which is having even higher wavelength, then what we can see is that we will be hitting again some other kind of absorption edges. So, this absorption curve of nickel, if we plot it for longer wavelengths from compared to 2.5 angstrom, if we go to higher and higher wavelength, then for nickel, this is for different material, don't get confused. So, don't look at the wavelengths here, this is for a different material altogether. But if we consider only for nickel, if we go beyond 2.5 in this direction, then what we will be seeing again few other discontinuities. Those are basically L, M, K, N, all of this higher order electronic shell or orbitals, higher order primary orbits, those absorption because of those electrons. So, that means in those cases instead of K electron, the X-ray photon will have sufficient energy to knock out an L, for example, L shell electron or M shell electron and so on, and the electronic transition happens between say L, between M and L shell, between N and L shell and so on and so forth. So, we have already discussed this. So, these are also, there also it is a true absorption, but the true absorption process is happening in terms of L shell and higher electronic states, not K shell is not involved there. So, that is why those processes, and we already discussed, since the energy of L shell is much lower than the K shell. So, those processes the energy will be lower, the energy involved or the energy required for the X-ray photon will also be lower, and they will be appearing at a longer wavelength. Okay. So, this absorption, for example, here you will be able to see 3 L. So, there is 3 electrons, 3 orbitals for L shell, and those 3 corresponding to those 3 orbitals, you will see 3 different discontinuities or 3 different absorption edges here. And this absorption edge, again it depends on the atomic number. We already see how the atomic number changes, or how the characteristic X-ray radiation depends on the atomic number according to Moseley's law, exactly the same way, because the same process is happening here. The same electronic transition is responsible for characteristic radiation generation, and the same electronic transition is responsible for this absorption edge. So, the dependence on the atomic number is also pretty much the same, and we can use this Moseley's law for calculating again the lambda k, that means the wavelength of absorption edge, the variation of wavelength of absorption edge with respect to the atomic number. So, heavier the atom, so shorter the wavelength for absorption edge. Same thing, heavier the lighter the atom, and the longer the wavelength for absorption edge, similar to the characteristic radiation. Same variation will happen in this case as well. Okay. So, now the relationship between absorption edge and characteristic radiation. As we said, these are pretty much the same process that is happening, but of course, there are certain distances. Already we have seen that there is a difference between the wavelength of the two. The wavelength of absorption edge is shorter than the wavelength of characteristic radiation, because of that energetics involved in these two things. Now, the absorption edge is easier to be measured, as I already said, that in order to measure the absorption edge, what we or the wavelength of the absorption edge can be very easily measured, because what I need to have is an experimental setup where I have an incident X-ray source or incident X-ray with a known wavelength, and I have to measure the intensity of that X-ray, and on the other side I have to measure the intensity of the transmitted beam. Then I can put it back here, and I can very easily calculate the mass absorption coefficient, and then if I change the wavelength of this incident X-ray. I can repeat this experiment, I can measure the intensity of the transmitted beam, and I can very well calculate this mu by rho, the mass absorption coefficient, and in the process I can very easily develop this entire graph, the mass absorption coefficient versus the wavelength of the incident X-ray. This I can very easily get it, and from here I can find out that absorption age very precisely. Experimentally I can find out the absorption age. So point is that calculation of absorption age or the wavelength of absorption age is much easier than calculation or finding out the characteristic radiation, wavelength of the characteristic radiation. It is experimentally, it is much easier to calculate the wavelength responsible for absorption age. So if we can do that, if we can measure this absorption age, wavelength of the absorption age, we can very well then convert it to energy, and we can construct an energy level diagram for the atom. That means we can develop that what is the Wk, Wl and so on. From there we can very easily calculate the characteristic X-ray wavelength, because then we know that if in the process of this electronic transition, if we have a characteristic X-ray radiation generation, what should be the energy difference or what should be the energy change that will involve. From there we can measure the wavelength. So that is what the importance of absorption age. By measuring the absorption age wavelength, we can experimentally, which is much easier, we can measure the characteristic X-ray radiation. Theoretically we can calculate that. We can construct this kind of energy level diagrams. Okay. Now in doing this, we start with the same thing what we discussed previously when we were discussing about the binding energy. Basically any atom, neutral atom, we consider it 0, ground state is 0, and then if an electron is lost from there, the atom goes in an excited state and it will have some positive amount of energy, because what we consider is some work need to be done to pull this electron away from positively charged nucleus. So this goes up to some positively charged state. If we have, for example, a k electron knocked out, then we will have a Wk amount of energy is there. We think that this much of energy or this much of work done needs to be done in order to knock out a k electron shell. Of course, then we can have a L electron going out, then we have Wl amount of energy required, Wm, which are smaller than Wk, because k electrons are much more tightly bonded, or the highest amount of binding energy is there for the k electron. So k electron Wk state, k state is highest. So there in the k state we have, I am sorry, here it should be k electron removed, here it should be L electron removed and so on. So this is a little mistake we did, but this k state is basically where the k electrons are removed. That means Wk, you provide Wk amount of work or energy in the system, in that atom, you remove a k electron, and we call that material now has gone to k energy state. Okay. Similarly, we can calculate L energy states where it is an L state where Wl amount of energy is required and you have an L electron removed and so on and so forth. Okay. Now if we consider that a k electron is removed from an atom, whether by incident electron or by X-ray, then the atom raised to the k state. Again, in that process, now the atom is gone to an excited state. When it tries to come back to the ground state, then an electronic transition will happen and the electron, let us say, moves from L state to k state. In the process, there is an vacancy created in the L shell, right. That means the atom, we can think of, the atom has now undergone from k state to L state. So understand this. So first we started with a atom, ground state atom. We create a k shell vacancy by either incident electron or by X-ray, whatever it is. It creates an k shell electron. The electron has gone to k state with an amount of energy stored in there. If we imagine that it's stored there, that is Wk. In order to fill out this vacancy, an L shell electron jumps to k shell, and in that process the vacancy is now transferred to L shell. That means in that process, the whatever energy is required to create that L shell vacancy, that needs to be there, that is stored. So that amount of energy, we can see that this is basically Wk minus Wl. So that much of energy is stored in the system. Now and this process, if it repeats slowly, the material should come back to its ground state. Okay. So, this when this L shell electron jumps back to K shell and the material goes from K state to L state, this will be accompanied by an emission of a K characteristic radiation. We have already seen how K alpha 1 generated K beta, K alpha 2, all of this. So, that basically this much of energy difference will lead to, for example, if I have this transition between L and K, I will be having a K alpha radiation here, characteristic radiation here. We have already seen this. Okay, so this is a little bit odd, this looks a little odd here. Okay. Anyway, so the wavelength of characteristic emission lines can be calculated from the difference in energy between the two states. If we consider that it is between K state and WK and WL, K and L state, and we are having an K alpha emission. So, we just consider that K alpha characteristic line, K alpha characteristic radiation is there. That means, the L level of an atom, we have an L shell, from an L shell an electron transfers to K state, and this normally K alpha 1 happens between transition between K shell and L3 shell. Okay. So, that electronic transition basically gives rise to this kind of K alpha 1 radiation. So, we can write this, if the frequency of this K alpha 1 or K alpha 1 radiation, which we write it nu K alpha 1, then the energy of that process in the of that K alpha 1 radiation, we can write it as H nu K alpha 1, which is equal to the difference between here, that is, this K alpha 1 energy is basically the difference between WK, that is the K state energy, minus WL, that is the L shell energy, and out of all the L shell, it is not all the L shell, it is L3 shell. So, this is equated to WK minus WL3. That means, here again WK, what we can write here is H nu K, and this nu K is the frequency for K absorption age. Okay. So, WK, that is the amount of energy required in order to create a K shell electron. Remember, in order to create a K shell electron, first you have to knock out a photoelectron, and in the process you have this radiation, this fluorescent radiation generation. So, that means, in the process basically you are creating a K absorption age, that energy will be exactly same as the absorption age, K absorption age energy, and correspondingly the same frequency and wavelength. And then similar thing for WL3. So, ultimately what you can write in the terms of wavelength, 1 by lambda K alpha 1 is equal to 1 by lambda K minus 1 by lambda L3. Here lambda K alpha 1 is basically the characteristic radiation, wavelength of the characteristic radiation, whereas 1 by lambda K, this lambda K is the wavelength of the absorption age, and this lambda L3 is the absorption age, wavelength of L3 absorption age. From here also what we can find out, or what we can check, is 1 by lambda K alpha 1. So, if I consider this relationship, 1 by lambda K alpha 1 obviously is less than 1 by lambda K, right. So, if I just consider here 1 by and from there what I can find out is the same relationship what I previously derived from energetic calculation. Yes, I have calculated this from energetics of this process. The same thing we can now discover or derive here from this relationship, that is the lambda of K absorption age, the wavelength where the absorption age appears will be at a shorter value, or that the shorter wavelength compared to the K characteristic radiation, the wavelength corresponding to K characteristic radiation. So, same thing we can derive again here, same analogy we can derive, and from there what we can derive again from this relationship, as I already said, measurement of these two are pretty easy. So, measuring this absorption age wavelength corresponding to absorption age, measurement of that is very easy, it's easier, much easier, and same thing we can measure the absorption age for L lines, and From this value, we can calculate the wavelength of this K characteristic radiation very precisely. Similar thing we can do to calculate the critical excitation voltage of this characteristic radiation, K characteristic radiation, and to excite K radiation, we know that electrons must have an energy equal to Wk. So, again we go by the same route, the energy of the electrons, which is given by E into Vk, where Vk is the excitation voltage, equals Wk, and that Wk is equals to again H nu k equals Hc by lambda k. Altogether finally it comes down Vk, the critical excitation voltage for generation of K characteristic radiation. This comes out to be this value 12.40 into 10 raised to the power 3 by lambda k. Now again this lambda k is the characteristic or is the wavelength of K absorption age. So we can find out not only the wavelength of K characteristic radiation, we can also find out the critical excitation voltage for generation of a K characteristic radiation. Fine. So one thing you must notice that the critical excitation voltage, the expression for critical excitation voltage is very similar to that we previously derived for short wavelength limit for a continuous spectrum, the short wavelength limit. So that also has this kind of a shape where 12.40, the same terms come here, and we have expressed here the short wavelength limit in terms of the voltage, and here we have derived the short wavelength limit or the critical excitation voltage in terms of the absorption, the wavelength of the absorption age. Basically all of these processes is pretty much the same. The way electrons are generated, the way X-rays are generated, the characteristic radiation generated, all of them or the way they are absorbed, basically all of this is related to electronic transition. That is why they pretty much looks very much the same. And because of the similarity between these two equations for lambda SWL and Vk, the same curve that we could generate for one, the lambda SWL with respect to the voltage, applied voltage, from the same curve we can derive the wavelength of the absorption age and vice versa. If we derive the wavelength of absorption age, from there we can derive the critical excitation voltage, and from there we can very well derive the lambda SWL, short wavelength limit. So we will be stopping here, and we will continue our discussion about this X-ray filters in the next class. Thank you.